At 04:22 hours local time, 15 Ukrainian FP1 drones were racing across occupied Crimea at 100 miles per hour, heading straight towards Syky Air Base, a place that would become a sea of fire within the next 90 minutes. There, Russian aircraft were being prepared for takeoff to carry out airstrikes against Ukrainian territory. The FP1s had exactly that much time to cross 150 miles of hostile airspace and strike them before they left the runway. The calculations showed it was possible, but only barely, and 35 miles to the north, a Russian Podlet K-1 radar operator was about to make those calculations much more difficult. Podlet K-1 combines mechanical scanning with digital electronic scanning. Its radar beam can jump from one angle to another in just a few millionths of a second. The operator watched a screen crowded with targets, a military convoy on the Simferopol-Yevpatoria route, a communication station near the coast, wind turbine blades turning steadily in the darkness, a flock of seabirds creating a weak signal that flickered and disappeared. 250 returns kept appearing with every sweep. Then one weak signal caught his attention in the northern sector 220 miles away. Moving south at 100 miles per hour, he leaned forward. At low altitude, the radar picked up almost everything: vehicles, birds, sea waves, terrain, and weather. The software filtered them using the Doppler effect, the same principle that makes helicopter rotor noise sound higher as it approaches and lower as it moves away. Stationary objects reflect at the original frequency and are filtered out. Moving objects remain on the screen, but a UAV flying at 100 miles per hour can produce a return almost similar to a military vehicle moving below. Even a flock of seabirds can be mistaken for a small aircraft skimming close to the ground. When a target appears in one sweep, disappears in the next, then reappears in a different position on the second scan, the system is forced to guess. In most cases, it will label the return as birds or terrain clutter. The operator can override that conclusion, but only if he has enough reason, and this time he did. There was no reason for any flight activity to appear in this area at this hour. The signal appeared again on the next sweep. Same direction of travel, same speed, 32 miles. His finger immediately moved toward the warning button. 18 miles to the south, a Su-24M was sitting on the runway at Syky Air Base. Technicians were carrying out final checks as bombs and missiles were mounted one by one beneath its wings. It would take off in 80 minutes. The window available to the FP1s was slowly disappearing. The third scan, the signal was still there, 32 miles. It continued moving south at a constant speed. The operator's finger stopped just above the warning button. One more clear confirmation, and he would report the target and wake up the entire air defense network protecting Syky. The phased array beam would automatically sweep up and down toward the north with extreme electronic speed. But this time the screen was empty. The signal had disappeared. The FP1s had just dropped lower and slipped into the terrain around Lake Sasak-Sich, a gap Ukrainian planners had identified on satellite imagery weeks earlier. The phased array of the Podlet K-1 swept the full circle while continuously steering its beam up and down, digging close to the ground and building a three-dimensional altitude map of every moving object. But Lake Sasak-Sich created a problem. The beam could scan down across the surface of the lake and continue touching the terrain beyond it. But the low pocket between the waterline and the lake shore remained hidden. The FP1s were flying precisely inside that gap. The operator waited. The fourth scan, nothing. The fifth scan, still nothing. Then a small dot suddenly appeared on the far side of the lake. One FP1 had changed altitude and risen out of the mask zone for a few seconds, but the track had been broken for too long. The computer immediately classified it as a bird, just another false return. The Russian radar crew had seen too many signals like that in the previous weeks. Seabirds, water surface clutter, and targets that appeared, disappeared, and led to nothing. Most of them never meant anything. But then the commander stared at the screen longer than usual. Something was wrong. The heading was too steady. The speed was too constant. A bird could not fly straight at 90 miles per hour across 3 consecutive scans. But the computer still marked it as wildlife. The track had already been interrupted while more than 250 other signals continued flickering across the screen. He looked at the clock. 0428 hours local time. He clicked his tongue and moved his hand away from the alarm key, waking the entire air defense network at this hour because of a signal the system had already identified, as a bird could leave the whole duty crew answering uncomfortable questions. Nothing unusual. For the next 6 minutes, the remaining 14 FP1s passed one by one through the same corridor over Lake Sasak-Sich, an approach route Ukrainian planners had studied on satellite imagery weeks earlier. The Russian military report recorded no hostile flight path. A system specifically designed to detect low-flying targets had just been defeated by a small gap between the lake surface and the shore, and by software that could not tell the difference between a weapon racing towards Siki and a seabird. Fuel remaining 65%, distance to Siki Air Base 70 miles. Time left before final checks and takeoff preparation 40 minutes. The FP1s had penetrated the first surveillance layer, but the operators in Kharkiv knew exactly what was waiting for them in the center of Crimea. Compared to the electronic warfare layer ahead, the Podlet K1 radar had only been the warm-up. The GPS indicator flickered. The coordinates jumped away from the flight path. Then the signal disappeared completely. The lead operator did not panic. He had been waiting for this moment. 12 miles east of Siki Air Base, a Russian Krasuka 4 system had just begun broadcasting wideband multifunctional digital jamming through a large steerable parabolic antenna array designed to electronically suppress its targets. It covered the area with a wall of electronic noise, suppressing the navigation, communication, and radar signals the UAVs needed to continue the mission. The satellites were still transmitting from orbit thousands of miles above the Earth, but by the time those signals reached Crimea, they were only a faint whisper. Krasuka 4 was screaming directly beneath them. Trying to receive satellite signals through that interference was like trying to hear the ticking of a wristwatch while standing beside a jet engine as it roared to life. The satellites had not disappeared. The FP1s simply could no longer hear them. This is how many UAVs are defeated. Once GPS is lost, ordinary aircraft no longer know their exact position, heading, or distance to the target. Commands from the operator can also be disrupted. The video feed freezes, coordinates drift, and the UAV begins slipping away from its planned corridor. Some will circle until they run out of fuel. Others will crash into empty fields before ever getting close to the target. But the FP1 was not built to depend entirely on GPS. It was built precisely for this moment. GPS did not simply disappear. It began to lie. On the control screen in Kharkiv, the coordinates of the FP1 formation suddenly jumped away from the flight path. The navigation system reported that the drones were drifting east, even though the compass, altitude, and nose heading all showed that they were still continuing south. The computer detected the anomaly almost immediately. The GPS data did not match the compass. It did not match the airspeed. It did not match the trajectory recorded only seconds earlier, so it rejected the satellite signal. The camera beneath the aircraft took over. The software began comparing ground imagery with the stored map. The curve of a lake, a railway line, road intersections, and residential areas stretching across the Crimean plain. Each landmark helped the computer correct its position. But then, low clouds covered the ground. 3 gyroscopes and 3 accelerometers immediately took over. They measured every rotation, every change in velocity, and kept the FP1s flying along the last confirmed heading. No GPS, no terrain image, only inertia, but inertial navigation has one weakness: drift. A gyroscope that is wrong by only 0.1 degrees ES, even while the UAV is actually flying straight, can create a false rotation of up to 36 degrees after 1 hour. An accelerometer offset by only 0.1 drem can also accumulate into phantom velocity, and from phantom velocity into distance that does not actually exist. If forced to fly on AN-196 alone for the full 90 minutes, positional error could grow to 5 to 8 miles, enough for an autonomous UAV to fly past the target without ever seeing it. The FP1s did not need AN-196 to stay accurate forever. They only needed it to hold the correct heading until the ground appeared again. A few minutes later, the cloud layer broke apart. The camera recognized the lake shore, the railway line, and the residential areas north of Siki. The computer immediately used those landmarks to pull the error back down. The lead operator recognized the terrain. He switched to live image piloting. From that moment on, The false coordinates no longer mattered. Krasuka 4 could keep jamming GPS, but it could not hide the roads, lakes, and buildings now clearly visible to the camera, fuel remaining 45%. Distance to target 22 miles. Position error 1 mile. The jamming system had made the FP1s lose GPS, but it could not stop them from reaching Siki. The attack window was still open. Then the global positioning system came back. The signal light changed from red to green. 4 satellites were locked. The coordinates stabilized. The operator in Kharkiv felt the tension rise. He immediately became suspicious. Krasuka 4 was still active. The FP1 formation was still deep inside the electronic suppression zone. There was no reason for the satellite signal to suddenly become clear. He looked down at the map screen. The global positioning system said the formation was 10 miles east of its actual position. But the camera told a different story. The road below curved west. A cluster of houses sat close to the railway line. The lakeshore appeared on the left side of the frame. None of those details existed at the coordinates the global positioning system was reporting. This was not jamming. Jamming makes the signal disappear. This was spoofing. A Russian transmitter on the ground was broadcasting signals designed to look exactly like real satellite signals. The structure was the same. The time code was the same. But the transmission timing had been altered. A global positioning system receiver calculates position by measuring how long it takes a signal to travel from a satellite to the unmanned aerial vehicle. Change the delay by only a few nanoseconds, and the position can shift by several meters. Stretch the error to a few microseconds, and the coordinates can be pushed kilometers away. The fake signal was stronger because it was not coming from orbit thousands of miles above the Earth. It was being transmitted from directly below the formation. An ordinary, unmanned aerial vehicle would believe those coordinates. Its autopilot would begin correcting the flight path, pulling it away from the target. If the altitude signal were also falsified, the unmanned aerial vehicle could believe it was flying hundreds of feet higher than it actually was. It would lower itself and crash into the ground without a single air defense missile being fired. But the FP1 did not rely on the global positioning system alone. While the satellite signal claimed the formation had shifted 10 miles, the gyroscopes recorded no turn. The accelerometers detected no change in velocity. The compass still pointed south. The camera image continued moving through the same flight corridor as before. No movement, no acceleration, no turn. An object cannot move 10 miles in a single instant. The computer marked the global positioning system data as irrational. Then it checked the signal source. Real satellite signals should arrive from multiple positions in the sky. Each satellite creates its own angle of arrival. But the newly appearing signals all arrived at the same time with the same strength from the same direction. They were not coming from 4 satellites. They were coming from one ground-based antenna. The system immediately cut the global positioning system out. The false coordinates disappeared. The camera and inertial navigation system continued the mission. The error circle began expanding again, but an imperfect position was still safer than a false coordinate the computer trusted completely. The detection and rejection process lasted 30 seconds. Only 30 seconds. But at Siki Air Base, every second mattered. The auxiliary power unit of the Su-24M began to start. Lights across the parking apron came on. Technicians removed the final testing equipment from the aircraft's fuselage. The bombs and missiles beneath the wings were ready, fuel remaining 38%. Inertial system error 3.5 miles. Distance to safety 18 miles. The attack window was closing. The operator pushed the throttle forward. Speed increased. Fuel began dropping faster. Ahead, the Su-24M was still on the ground, but the runway had begun to wake up. The operator had only about 10 minutes left. After that moment, the Su-24M would leave Siki Air Base, and the attack would shift from a stationary target into an almost impossible pursuit. He switched the camera to artificial intelligence target recognition mode. The computer vision system began scanning each frame, comparing the shapes appearing below with the stored target library, hangar rooms, fuel trucks, weapons racks, the fuselage and wings of the Su-24M. The image feed came back at 30 frames per second. 3 seconds with nothing. 4, 5. Then the algorithm locked onto the target. Outside a hangar at Siki, bombs and missiles had already been fully mounted beneath the wings of the Su-24M. Technicians were removing the final test cables. A towing vehicle had reversed into position, ready to move the aircraft toward the taxiway. The Su-24M was being prepared for a bombing mission against Ukrainian territory, which Russia described as a response to repeated attacks on Crimea. If it took off, the bombs and missiles beneath its wings could strike military targets and infrastructure deep inside Ukraine. But then the situation changed. The inspection ended earlier than expected. Senior officers left the parking area. Ground personnel began clearing equipment. 2 pilots wearing flight helmets walked quickly toward the aircraft. Time was no longer being counted in minutes. It was being counted in seconds. The operator had 2 choices: strike the hangar roof immediately. The target was large, stationary, and easy to hit, but the concrete structure could absorb much of the blast, leaving the Su-24M inside with only light damage. Or wait until the aircraft was pulled completely outside, entered the taxiway area, and strike when there was no longer any protective cover. The second option could destroy the Su-24M along with all the bombs and missiles beneath its wings, but it required far greater precision, and every second of waiting brought the Russian aircraft closer to the runway. The operator made his decision: wait for the Su-24M to leave the hangar area. It sounded simple. Carrying it out was far more difficult. Most attack unmanned aerial vehicles are programmed to fly to a fixed set of coordinates: a hangar, a fuel depot, a radar station, or an aircraft parked on the ground. But the Su-24M was about to be towed onto the taxiway. From that moment on, the target would be constantly changing position. If the FP1 struck the old coordinates, it would hit nothing but an empty section of concrete. But the FP1 still maintained a direct link with the operator until the moment of impact. The camera in the nose of the unmanned aerial vehicle transmitted live images, allowing him to continuously adjust the flight path according to the actual movement of the fighter. He was not aiming at where the Su-24M was standing. He was aiming at where it was about to go. The FP1 formation dropped to an altitude of 50 feet, skimming close to the terrain to avoid most of the radar protecting the base. At that distance, the unmanned aerial vehicles were little more than small black shapes racing through the pre-dawn sky. Inside the Su-24M, the pilot had no idea that a threat was approaching. The aircraft systems showed normal status. The fuel had been loaded. The bombs and missiles had been secured beneath the wings. The final checks were being completed before the fighter moved toward the main runway for takeoff. For the pilot, these were only the last minutes of a familiar launch procedure. For the operator in Kharkiv, they were the final window to destroy the target. The 15 FP1 unmanned aerial vehicles split into 3 groups. The first group turned toward the aircraft hangars. Their mission was not only to cause damage, but to force Russian air defense to turn its radar and firepower in the wrong direction. The second group drove toward the fuel depot. If they struck it, the resulting fire would block visibility, create chaos across the airfield, and disrupt every takeoff operation. The third group continued straight toward the Su-24M. On the screen, the fighter began to move. The towing vehicle pulled it out of the sheltered area and toward the taxiway leading to the main runway. The operator made a slight adjustment on the control stick. The lead FP1 changed direction with the target. Fuel remaining 19%. Distance 560 feet. The aiming point slid across the tail, moving gradually toward the fuselage and the bombs hanging beneath the wings. Behind it, the other FP1 unmanned aerial vehicles were closing in from different angles. The Su-24M continued rolling toward the runway. The pilot did not see them. The video ended just before the first FP1 slammed into the target. They had been detected. The 1RS-11 radar of a Panzer S-1 system picked up 5 FP1 unmanned aerial vehicles racing straight toward the Su-24M. Distance 2 miles, altitude 50 feet, closing speed 90 miles per hour. On the radar screen, 5 small returns appeared against the layer of ground clutter. Their flight path left no room for doubt. The target was the Su-24M. The gunners switched to the electro-optical system and locked the targets with the thermal camera. The two 2A38M automatic cannons immediately swung toward the incoming formation. They opened fire. The two 30mm guns began spinning rounds at a rate of 5,000 rounds per minute. The ammunition used programmable airburst fuses designed to detonate near the target instead of requiring a direct hit. Each burst released around 400 steel fragments within a radius of nearly 13 feet, creating overlapping clouds of shrapnel directly in front of the unmanned aerial vehicle formation. The lead FP1 disappeared in a white flash. Steel fragments tore through its wings and engine. The second tried to break right, but flew straight into the next kill zone. The image from its camera shook violently, then went black. 2 had been shot down. The remaining 3 immediately split directions. 2 continued driving toward the Su-24M, forcing the gunner to rotate the turret and keep fire focused on the corridor leading to the runway. The third FP1 climbed to 350 feet in 3 seconds, rising above the fragmentation cloud ahead. While the Panzer focused on the 2 targets threatening the fighter, it swung around the flank and then dived back down close to the ground. That was where geometry began to turn against the Panzer S1. The turret could only depress its guns to about -5 degrees. When a target flies extremely low and gets too close, it slips beneath the minimum firing angle. The radar can still know the target is there, but the guns cannot depress any farther to follow it. The gunner tried to swing the turret. Too late. The FP1 had dropped below 30 feet and was now charging straight at the air defense system. The 2 gun barrels stopped at their mechanical limit, pointed at a spot above the unmanned aerial vehicle's actual flight path. Distance 300 feet, 150, 50. The FP1 slammed directly into the Panzer S1. A violent explosion engulfed the combat cabin before the gunner could fire the next burst. The radar went dark. The turret froze in place. The final defensive layer protecting the Su-24M had just been taken out of the fight. No more anti-aircraft guns. No more fire control radar. Only Russian soldiers below raising AK-74 rifles and firing wildly into the pre-dawn sky. On the taxiway, the 2 pilots immediately abandoned the cockpit. They jumped onto the tarmac and ran from the Su-24M as the final 2 FP1 unmanned aerial vehicles continued their attack. At this moment, fuel remaining 5%, engine endurance about 1 minute. There was no longer enough fuel to circle back. There was no longer any chance to correct a failed approach. The control team in Kharkiv sent the final order to all 3 groups. Attack simultaneously. At 0552 hours local time, the monitoring screens at Siki Air Base turned white. The first strike hit the hangar area on the northern side of the airfield. 1 FP1 punched through a partially open steel door and exploded inside. The enclosed space trapped most of the pressure, causing the shock wave to rebound repeatedly between the roof, the floor, and the concrete walls. The first explosion. Metal panels were blown off the hangar frame. Glass and nearby structures shattered into thousands of fragments. A maintenance vehicle near the entrance was flipped onto its side, blocking the access route for rescue crews. The first column of smoke had barely risen above the hangar roof when the second strike appeared at the opposite end of the base. The FP1s heading for the fuel depot were not aiming at the center of the storage tanks. They were aiming at the valve and pump cluster near ground level. That was where fuel was transferred from the tanks into the pipeline system leading to the parking apron. Destroying 1 tank would eliminate the fuel inside it. Destroying the distribution cluster could make the entire depot unable to operate. The lead unmanned aerial vehicle struck the main pipeline. Metal was torn open. Aviation fuel sprayed out under high pressure, forming a fine mist across the pump area. Another FP1 arrived a few seconds later. The second explosion. The fuel mist ignited almost instantly. A fireball expanded through the pipelines, swallowing valves, cables, and control equipment. Temperatures inside the burning zone could quickly exceed 1,600 degrees Fahrenheit, hot enough to make steel lose strength, melt rubber seals, and begin deforming pipe joints. Pressure inside one pipeline, not yet sealed by the valves, pushed more fuel into the fire. The flames did not die down. They fed themselves. In less than 10 seconds, 2 distant areas of the base were sending emergency signals at the same time. Fire crews were forced to split their forces. Specialized vehicles left their runway protection positions and turned toward the 2 spreading fires. That was when the final 2 FP1s entered, The Su-24M sat in the middle of the taxiway, no longer protected by the hangar. Its nose was angled toward the runway. Beneath its wings were the weapons prepared for the upcoming mission. The first FP1 adjusted slightly left. Fuel remaining 3%, distance 400 feet. The camera kept the aiming point on the aircraft's nose, where the navigation radar, mission computer, and electronic systems needed to detect, track, and attack targets were concentrated. 200 feet, 80 feet. Impact. The warhead detonated through the forward skin, crushing the radar compartment and severing the bundles of electrical wiring running back toward the cockpit. The nose of the Su-24M folded downward, but the center fuselage and fuel tanks had not yet caught fire. The second FP1 continued its attack. Its engine began losing power. The fuel indicator dropped below 1%, but the target was already too close. At nearly 90 miles per hour, the unmanned aerial vehicle still carried enough kinetic energy to cover the final distance, even if the engine stopped producing thrust. The aiming point shifted away from the cockpit. It stopped at the wing root, the third explosion. The blast tore through the fuselage near the fuel system. Fuel vapor inside ignited, creating a stream of fire that swept along the wing and entered the engine compartment. Only seconds later, the flames reached the weapon's pylons. A secondary explosion rolled across the airfield. The fuselage lifted off the landing gear, then dropped back onto the taxiway. Fragments of light alloy were thrown hundreds of feet outward. The weapon-carrying section of the wing disappeared behind black smoke and orange fire. In less than 1 minute, 3 critical points at Siki Air Base had been hit. The hangar area could no longer receive aircraft. The fuel distribution system had stopped operating, and the Su-24M, prepared for a bombing mission, had become a blackened wreck directly in front of the runway. The greatest damage was not only the destruction of one aircraft. Russia would also have to inspect the entire fuel depot, clear the taxiway, assess the weapons exposed to heat, and move the remaining aircraft to dispersed positions. Every hour the base remained out of operation was another hour in which missions from Siki were delayed or canceled. The attack also revealed a more serious problem. A base with surveillance radar, electronic warfare, and short-range air defense could still be disabled when multiple unmanned aerial vehicle groups struck different functions at the same time. One group created the emergency. One group cut the fuel supply. The final group eliminated the primary target. 5 Ukrainian unmanned aerial vehicles were racing across the airspace over the Crimean Peninsula when everything suddenly went dark. The global positioning system disappeared. The control link was cut. On the screen, only wildly shifting coordinates remained along with an invisible wall of electronic interference. What happened next seemed almost impossible. At the same time, 7 other AN-196 Lyutyi unmanned aerial vehicles were circling over the central Black Sea, moving toward the Kerch Strait. Their target was clear: a 35-car military supply train loaded with fuel, artillery shells, and weapons. After days of continuous Ukrainian strikes and isolation, that train was nothing less than the last lifeline for Russian forces in Crimea. But Russia was not going to let Ukraine's plan unfold so easily. Russian electronic warfare systems had taken away the navigation system, jammed the signals, and cut off the sensors. What the Russian air defense crews did not know was that Ukraine already had a plan to overcome that system. They were using a tactic Russia had never expected. To reach the Russian supply train, the first step was to destroy its air defense protection. If they missed, all 12 unmanned aerial vehicles would become little more than live fire practice targets. If they hit, the warning network in the area could be blinded for 20 minutes. But between them and the target stood one of Russia's most modern defensive systems, Borisogledsk-2, an electronic warfare complex trying to jam communications, distort navigation, and push the entire formation off its flight path. Inside the Borisogledsk-2 command vehicle, Russian operators watched every signal line appearing on the screen. The system scanned the entire electromagnetic spectrum, identified the direction of transmission, and then concentrated jamming power on Ukraine's communication channels. Within seconds, the control signals were drowned in a sea of interference. The Russians expected the AN-196 Lyutyi unmanned aerial vehicles to lose control, turn back, or crash into the ground. But they waited in vain. The unmanned aerial vehicles did not stay on one frequency long enough for Borisogledsk II to lock onto them. Every time the Russian system managed to suppress one channel, the signal had already shifted to another. And when the final link was cut, the onboard computer immediately switched to inertial navigation and continued following the preloaded route. Russia could silence the signal, but it could not erase the path already stored in their memory. Meanwhile, the formation of 12 AN-196 Lyutyi unmanned aerial vehicles had split into two directions. The northern group continued, flying deep across the Crimean Peninsula toward the Sea of Azov, while the southern group began from the central Black Sea and moved toward Kerch railway station, extending its route in order to approach the Kerch Strait from the opposite direction. Ukrainian intelligence had identified the positions of radar stations across the area, then combined terrain, the curvature of the Earth, and the limits of the radar horizon to find blind corridors wide enough for unmanned aerial vehicles to penetrate. But staying inside that corridor at nearly 150 miles per hour was like threading a needle in the sky. If the southern formations arrived just a few minutes too early or too late, it would enter the engagement zone of the S-400 system. If it drifted away from the programmed flight path, Buk M3 batteries near the Kerch Straits could detect it and shoot the unmanned aerial vehicles down one by one before they had time to link up. So, the northern group deliberately flew slower and allowed its signal to appear more clearly. It acted as the decoy, pulling Russian radar and air defense firepower toward the peninsula. While the combat crews focused on tracking those targets, the southern group dropped to only 50 feet above the sea surface, slipped beneath the radar horizon, and raced toward the Kerch Strait to form a pincer movement. The plan began to work. On the command screen, the Russians saw one group of unmanned aerial vehicles advancing from the north, but they could not be certain whether it was the main attack force or only bait. They were forced to choose: concentrate all air defense to the north and leave the seaward approach exposed, or divide their forces and face the risk of both groups breaking through at the same time. They had only a few seconds to decide. By 0715 hours local time, Oscar on the first aircraft produced a false match. The algorithm identified a bend in the river below and matched it with a different location on the map. The calculated coordinates were hundreds of yards away from the actual position. Under normal conditions, the global navigation satellite system would reject this result. But the satellite signal had been interrupted. Telemetry was completely lost, and the inertial navigation system had also accumulated error after hours of flight. So the computer accepted the false result. The unmanned aerial vehicle changed course by a few degrees to correct an error that did not exist. The following terrain matches continued pushing it farther away from the mission corridor. The second aircraft also misidentified a forest strip and the road below. Two Lyutyi unmanned aerial vehicles began separating from the formation. One drifted west, the other drifted east. By the time Oscar detected that the data was no longer consistent, both were several miles away from the target route. The control system marked the deviation as uncorrectable, locked the flight controls, and directed both aircraft toward empty farmland. They crashed into fields far from residential areas, their warheads failing to detonate. 5 AN-196 Lyutyi unmanned aerial vehicles remained on course, fuel remaining 18%. Distance to Podolsk 28 miles. Flight time 16 minutes. They were now entering the final approach corridor, approaching the logistics hub from the south at an altitude of 200 feet. At 0728 hours local time, the air defense network around Moscow finally established a stable track on the 5 incoming targets. A short-range Pantsir S-1 system deployed near Podolsk turned its fire control radar toward the corridor. The 230mm 2A38M automatic cannons opened fire at a distance of 1.5 miles. High-explosive airburst rounds detonated ahead of the formation. Steel fragments tore through the composite wing of the lead aircraft. It spun out of control and crashed near an industrial railway line 2 miles south of the target. The remaining 4 aircraft did not change course. They did not attempt evasive maneuvers. The flight computer kept them locked onto the coordinates stored in memory. At 0731 hours local time, the 4 AN-196 Lyutyi unmanned aerial vehicles reached the outer perimeter of Russia's largest logistics hub in Podolsk. On the control screens in Kharkiv, the final update packet appeared. Altitude 120 feet, speed 115 miles per hour, target locked. The first Lyutyi dived directly into the central ammunition depot. The 150-pound high-explosive warhead detonated inside the primary storage bay, igniting stacked artillery rounds and rocket propellant. A massive secondary explosion tore off the reinforced roof, sending a shockwave across the entire facility. 3 seconds later, the second aircraft struck the fuel distribution complex 400 YD to the north. Thousands of gallons of diesel and gasoline erupted into a wall of flame, destroying the automated pumping stations and severing the main pipeline feeding supply convoys bound for Crimea. The third and fourth Lyutyi unmanned aerial vehicles struck the vehicle maintenance workshops and the secondary weapons storage building simultaneously. Within 90 seconds, the Podolsk logistics hub, the primary supply artery for Russian forces operating in the southern theater, was transformed into a raging inferno. Thick black smoke rose thousands of feet into the sky over the Moscow region. Visible for miles, the operation demonstrated a fundamental shift in modern warfare. By synchronizing cheap decoy swarms with long-range autonomous strike platforms using optical terrain-matching navigation, deep logistics networks, hundreds of miles behind the front line, can be systematically dismantled without relying on satellite guidance or real-time operator control. For the Russian military architecture, the vulnerability of critical supply hubs like Podolsk revealed that even the most densely protected rear areas can no longer offer guaranteed security against coordinated autonomous deep strike operations.